Hello, everyone, and thank you for joining in today. This is Mohamed Elsabagh from Kryptowire, and today I'll be presenting to you our work on FIRMSCOPE, a system that we developed to automatically detect privilege-escalation vulnerabilities in pre-installed apps in Android. This work was done in collaboration with Ryan Johnson and Angelos Stavrou from Kryptowire, and Chaoshun, Qingchuan, Zhao, and Zhiqiang from The Ohio State University. So this is a simplified view of the architecture of Android. You have the Android kernel and USENIX at the bottom, and then you have the Android runtime and framework on top of that, and then you have applications running on top of the framework. And Android apps, by default, are sandboxed. This is kernel enforced. They get isolated processes, private isolated storage in the file system, and they can exchange messages using a secure RPC mechanism. Also, access to the operating system and peripherals is protected by a permission model. Android apps in general can be categorized into two groups. There are user apps and there are system apps. So user apps are typically apps that you install from the market. They are low privileged, they can't do much. They can be granted some sensitive permissions, but the user would have to explicitly grant them these permissions. On the other hand, you have system apps which come pre-installed on the device. They are persistent, so they cannot, typically cannot be uninstalled. Some of them can be disabled, even though that's not the general case. They are highly privileged, and this is by design because of these services that they offer. For example, telephony and package management. They get access to more permissions than user apps. And a lot of times, these permissions are also automatically granted by the system. And there are many sources these pre-installed apps come from. In a typical Android device, you have the Android open source project and perhaps Google Apps. And you also have pre-installed apps that come from vendors who are also the firmware signers and chipset manufacturers, affiliates, and also carriers. All these apps are pre-installed and pushed to a device prior to reaching the end user. And if you look at a typical Android device, perhaps in late 2019, you'll see that there are 164 pre-installed apps in average versus only 30 user apps. So the attack surface from pre-installed apps is quite large. To give you a concrete example, this is the package installer, which pretty much every single Android device has one of these. And as you can see, it cannot be uninstalled and it cannot be disabled. And the system tells you that, hey, this package installer does not, request any permissions. However, if you actually dump the package information, you will see that it requests 22 permissions. A lot of them are sensitive, not available to third-party apps or user-installed apps, and all of them have been automatically granted by the system already. So whenever we speak of privileged functionality, access control comes to mind, right? So if you have a system or an app or a component that's offering something privileged, then you need to employ some sort of access control to prevent abuse of that functionality. And a typical access control protocol guarantees authentication, authorization, and accounting. So you know who's allowed access, what they are allowed to do, and you also keep a log of who did what. In the case of the package installer, you would expect that, okay, Google Play, which is a market app, yes, perhaps that's allowed to install apps, so you would expect the package installer to grant that to Google Play. Whereas if another random user-installed app tries to silently install apps in the background, you'd expect the package installer to reject that request. Unfortunately, that's not necessarily the case, and we found thousands of instances of privilege-escalation vulnerabilities in Android versions 4 to 9, all primarily due to improper access control in pre-installed apps. And this is a real example of one of the cases that we identified. It's an app called Lovely Fonts. It actually goes by many other names. And it consists of two separate apps. One is user-facing and another app that runs in the background. So both of them cannot be uninstalled, as you can see. One of them can be disabled, the user-facing part. And both of them are, of course, pre-installed apps. And all the sensitive functionality is actually implemented in the background part. And what we found is that this Lovely Font service, the background component of this app, has multiple local and remote command and code injection vulnerabilities that pretty much allows any actor on the device or on the network to execute arbitrary commands and arbitrary code in the context of the lovely font service process, which is a privileged process without user consent. So pretty much like a command and control channel. And we found this on more than 40 devices from more than 10 vendors, and of course impacting millions of users. So how did we do that? So that's our workflow of FIRMSCOPE. It has two stages: a pre-processing and a static taint analysis stage. In the pre-processing stage, we unpack firmware images, we extract and canonicalize apps, then we disassemble them, translate them into an intermediate language. And then for static taint analysis part, we build into procedural control flow and data flow graphs, and then we perform custom taint analysis with the help of analysis rules that steer the analysis to detect specific classes of vulnerabilities. Of course, this is not without challenges. So in the pre-processing stage, the main challenges that we met were that Android images or ROMs lack standard formats. So you get ROMs in many different formats and different build and optimization settings and different file structures and so on. And also you have the disassembling stage. You have the Dalvik byte code itself, which in many instructions is close to 200 and maybe 50 instructions or so, which are a lot and they are complex instructions. So our solution to that was to implement different heuristics to try and unpack as much as possible from a firmware image. And instead of directly operating on the Dalvik byte code itself, we translated to an intermediate language that we developed that facilitates the analysis and makes it a lot easier and abstracts out a lot of the internals of the bytecode that are perhaps not necessarily relevant to the analysis. For the static taint analysis stage, the main challenges that we faced were data that flows through fields and callbacks and life cycles and so on, which are common on Android, and also how to balance the analysis sensitivities that the analysis guarantees and runtime considerations. And this is important because we wanted FIRMSCOPE to be meaningful. So we were aiming at testing hundreds of thousands of apps. So that requires FIRMSCOPE to be both accurate and at the same time efficient. And our solutions to that, to these challenges, were to modify diffuse analysis to actually cover fields as well. So we track reads and writes through fields. And we also developed multiple graph gadgets that we use in our construction of the control flow and data flow graphs, where we encode as much information as possible into the graphs, such that taint analysis reduces to just a simple pathfinding problem, which we know very well how to parallelize and how to do efficiently. And then for the sensitivities that could not be guaranteed during construction time, we validate those in a post-processing or a post-validation stage on the paths that were discovered through the graphs. That way we achieved both accuracy and efficiency at the same time. And you can read more about this in the paper. Finally, for the rules, we implemented different rules that detect different classes of privilege escalation, including command and code injection, app installation, device recording, and so on. And most of these rules are like standard source sync taint analysis rules, but also a number of them are custom plugins using APIs that we export from the analysis. And again, you can read more about this in the paper as well. All right, so we scanned 2017 Android images spanning Android 4 to 9. I believe more than 50 or 100 vendors, totaling 331,000 pre-installed apps. And we found that 77% of these images contain at least one vulnerability. In total, we found more than 3,000 vulnerabilities, 850 unique vulnerabilities. And we found that 41% of the ROMs contained at least one command injection vulnerability. And if you look at this, you'd see these results. You'd see that about 1/3 of the vulnerabilities can actually lead to some form of code execution, which is a quite large percentage. So we only focused on findings that we had for Android 7, 8, and 9, and we disclosed more than 370 of those. And so far, we have received more than 200 confirmations from vendors, and fixes, and some of them have been fixed, and some fixes are in preparation. So who's to blame for this? We found that 92% of the weaknesses were introduced by vendors, and we actually found that a lot of the code that vendors add is really has a lax security posture. For instance, they add sensitive components, for example, that manage updates or manage the device itself, or helpers for the custom drivers and so on, sometimes without any sort of access control. We also found that the devices that tend to be closer to ASP, meaning they have less customizations, also tended to contain fewer weaknesses. In regard to runtime, we incurred about 7 minutes per app on average, only 53 seconds median. And for the full image analysis, we take about 81 minutes per an Android image, again 51 minutes median. So there is a tail to these distributions. For accuracy, we actually performed significantly better than prior solutions. We incurred less false positives and false negatives, and significantly less runtime overhead as well in regard to both CPU and memory consumption. And you can read the details in the paper. So to summarize, we developed FIRMSCOPE. It's an accurate, and efficient, and meaningful static taint analysis system. We applied it on 2017 Android images, 331,000 pre-installed apps. We detected 850 unique privilege-escalation vulnerabilities, more than 3,000 total. And we responsibly disclosed them for Android 7, 8, and 9. If you are a vendor and you're interested in trying FIRMSCOPE, please contact us. We do offer pilots. And thank you.